All right, welcome back everyone for another deep dive. This time we're getting into something that might seem super basic at first, but it's actually a sneaky little area where a lot of senior software engineer candidates trip up during those technical interviews.
Oh, yeah, definitely. I mean, we're talking about something that everyone uses every day, arithmetic in Java.
Exactly, it's like, plus minus divide, right? Shouldn't be too hard.
Right, but those interview questions dig deep,
Yeah,
They
right.
want to see if you really, really understand the nuances, like the little things that can cause massive headaches down the line if you're not careful.
So we're going to get into the nitty-gritty today. We're going to use some of Horstman's work, specifically chapters 1 through 4a of his book.
Yeah, the part about operators and types and all that.
Perfect. So the mission here is to basically extract the stuff that's most relevant for those senior level interviews. Like how can you show that you're not just some code monkey who can sling a for loop?
Right, right. It's about demonstrating a deep understanding of how things work under the hood, showing you can anticipate problems before they bite you and write code that's bulletproof.
Exactly. Let's dive into it then. First up, let's talk about Java operators. Now, we've all seen that big table in Horstman's book, Table 1.3, right?
Yeah, the one with all the precedence and associativity rules. Super important stuff, actually.
Absolutely. It's one of those things that you might gloss over when you're learning, but then it comes back to haunt you in the weirdest ways, especially in an interview setting when they throw some curveball expression at you.
Exactly. They want to see if you can handle something like, say, 3 plus 4, and then you have a left shift 5.
So what happens there? I mean, does it add first or does it shift?
So addition has higher precedence than the left shift, so it groups those together first. So it's like parentheses 3 plus 4, close parentheses, and then left shift 5.
Okay, so you end up with what, 7 left shift 5, which is
224. But the point isn't just the calculation, it's recognizing that precedence matters. Like imagine you're debugging some ancient code and you hit this massive expression.
Yeah, no parentheses to guide you. Nightmare.
Right, it's a nightmare. So you need to know those precedence rules cold to figure out what's actually happening.
And it's not just the order of operations, right? There's also this thing called associativity.
Oh, that's a good one. So associativity tells you how operators at the same precedence level are grouped. Like with subtraction, it's left associative. So if you have 3 minus 4 minus 5, it goes left to right.
Okay, so it's like parentheses 3 minus 4, close parentheses, then minus 5.
Exactly, which gives you -6. And then you've got right associativity, which works the other way around. Like with compound assignment operators, like I minus equals j minus equals k.
That's where it gets tricky.
Yeah, so it evaluates j minus equals k first, and then the result of that is used for I minus equals.
Right. I could see how that could trip people up, especially if you're not used to thinking about it explicitly.
And for a senior engineer, this matters. Big time. I mean, think about API design, right? If you're chaining operations and you don't understand associativity, you could get some really nasty side effects.
All right, so moving on. Let's talk about the assignment operator itself.
Yeah.
X equals expression semicolon. Seems pretty basic, right?
It does, but it's got this little quirk that can throw people off.
What's that?
The assignment itself returns a value, like the value that was just assigned.
Okay, interesting. So what, you can use it in like a nested expression or something?
Exactly. You see it a lot with things like input, where you're reading from a stream. So you'll have something like parentheses next equals in dot read, close parentheses, not equal to -1.
Okay, so walk me through that.
Sure. First, in dot read happens, that reads a value, then that value gets assigned to next, and then, get this, that assigned value is used for the comparison with -1.
Oh, so it's like a shorthand way of doing two things at once.
Yep. It can be super convenient, but it can also make code harder to read if you're not expecting it. And that's something that interviewers might throw at you, to see if you understand those subtle details.
And it reminds me of compound assignment operators. Those shorthands like plus equals and minus
Oh,
equals.
yeah. Those are just syntactic sugar, really.
Meaning?
Just a shorter way of writing something like amount minus equals fee. That's the same as amount equals amount minus fee.
Right. But using the shorthand makes it a bit cleaner.
Yeah, it's idiomatic Java. It shows you know the language well, which is important at the senior level.
All right, let's get to the fun part. The basic arithmetic operators. Plus, minus, multiplication, division, modulo.
Classic. Although division in Java, that's where it gets a little bit spicy.
Oh, yeah. I remember Horstman talking about that. The whole integer division versus floating point division thing.
It trips people up all the time.
Yeah.
So If both of your operands for division are integers, Java is going to do integer division.
Meaning it just chops off the decimal part.
Exactly. So like 17 divided by 5, you get 3.
Right. But if at least one of those numbers is a floating point type, then
you get floating point division. So 17.0 divided by 5, that gives you 3.4.
Okay, so knowing the types of your operands is absolutely crucial here.
Oh, absolutely. It's like one of the first things an interviewer will ask about. They want to see if you understand how data types impact your calculations and, whether you're aware of potential data loss.
And what about that classic edge case, dividing by 0?
Ah, yes. So with integers, dividing by 0 throws an exception, like a big, fat arithmetic exception.
Which, if you don't catch it, can crash your whole program.
Exactly. But with floating point division, you get infinity, or nan,
Right.
not a number. It's basically a special value that represents an undefined or unrepresentable result.
So, no exception in the floating point case, but you still have to be careful about how you handle those special values.
Right. And as a senior engineer, that's what they want to see. Can you anticipate these issues? Can you write code that's robust and won't just crumble under edge cases?
Okay, let's talk about modulo then. The percent sign gives you the remainder of a division.
Yeah, like 17 modulo 5 equals 2. Pretty straightforward.
But there's something about negative operands that can get tricky.
Oh, yeah, that's a fun one. So Horstman talks about how in some languages, the result of modulo with negative numbers can be implementation dependent.
Meaning it could vary from one Java version to another, or even one compiler to another.
Potentially, yeah. And even in Java, if you have, say, n modulo 2, and n is a negative odd number, the result might be -1.
So you have to be really careful when you're working with modulo and negative numbers.
Exactly. It's one of those things that can lead to subtle bugs, especially if you're not expecting it.
Which is why Horstman suggests using math.floormod in certain situations.
Yeah, it's a much more predictable way to handle modulo, especially when you might be dealing with negative numbers. Like, think about something like clock arithmetic, where you want to wrap around a value within a certain range.
Okay, give me an example.
Sure. Let's say you have a clock face with 12 hours, and you want to calculate a new position based on some adjustment. You could use the standard modulo operator, but if your position plus adjustment ends up negative, you might get a negative result, which doesn't make sense on a clock face.
Right, you'd want to wrap it around to the positive side.
Exactly. So you could do some extra calculations to handle that, but math.floormod takes care of it for you. You give it the position plus adjustment and the divisor, which is 12 in this case, and it always gives you a result between 0 and 11.
Much cleaner.
Yeah, and it shows that you're thinking about those edge cases, which is what senior engineers do.
Okay, let's move on to increment and decrement operators.
Yeah.
The good old plus, plus, and minus, minus.
Classic stuff, but with a twist.
Right, because there's the prefix version and the postfix version. And they both change the value, but they do it slightly differently.
Exactly. The core idea is the same. You're either adding one or subtracting one, but the key difference is what value they return in an expression.
Okay, break that down for me.
So with n++, the postfix version, it returns the current value of n before incrementing it. But with ++n, the prefix version, it increments n first and then returns the new value.
Ah, I see. So the order matters big time.
Yep. Classic example is when you're iterating through an array. Like string arg equals args bracket n plus semicolon.
Okay, so what happens there?
So it grabs the element from the args array at the current index n, and then it increments n for the next time around.
So if you use the prefix version there, you'd end up accessing the wrong element?
Exactly. And interviewers love to throw these little gotchas at you. It tests your attention to detail, your understanding of operator behavior.
Now, Horstman mentions that it's often better style to just use separate statements for incrementing and decrementing, even if it means a bit more code.
Yeah, it can make the code more readable and easier to understand, especially in more complex expressions where those side effects can get lost.
Okay, let's talk about the math class. It's packed with all sorts of useful stuff.
Definitely. Whenever you need something beyond basic arithmetic, math is your go-to.
Like what?
Well, Java doesn't have a power operator, so if you need to raise something to a power, you use math.pow.
Right. And there's a square root function, math.squart, and min and max for comparing values.
Exactly. And it also has all the trig functions like sine, cosine, tangent, and their inverses, plus logarithms and exponentials, and of course, constants like pi and e.
But for senior level stuff, There are these methods called the exact arithmetic methods that are really important to understand.
Oh yeah, these are crucial for writing code that's truly robust. See, the normal operators, they can silently overflow.
Oh,
Yeah, like if you try to multiply two huge integers, the result might wrap around and become negative. And there's no warning, no exception, nothing.
that sounds dangerous.
It is. But the exact methods, they throw an exception if an overflow happens.
So you can catch it and handle it properly.
Exactly. It's all about preventing those silent failures that can be a nightmare to debug.
Okay, so what are some of these exact methods?
Well, you've got math.multiply_exact, obviously.
Okay.
But there's also add_exact, subtract_exact, increment_exact, decrement_exact, and negate_exact.
Wow, that's a lot. And they all throw an exception if something goes wrong.
Yep. And they have versions for both int and long. So, as a senior engineer, you'd use these in situations where accuracy is absolutely critical.
Like financial calculations or anything with high precision.
Exactly. And it shows the interviewer that you're thinking about those potential pitfalls, that
Yeah.
you're not just blindly throwing operators around.
Now, Horstman also mentions these unsigned arithmetic methods in the integer and long classes.
Yeah, those are a bit more niche, but it's good to know they exist.
When would you actually use them?
Mostly when you're dealing with data that's inherently unsigned. Like
Right.
maybe you're working with some low-level system or a network protocol where values are represented as unsigned integers.
And using the standard signed arithmetic would mess things up.
Exactly.
Yeah.
So Java provides these special methods to handle unsigned arithmetic correctly, like compare unsigned, divide unsigned, remainder unsigned, things like that.
Okay, good to know. Let's move on to type conversions. Java does a lot of these automatically, right?
Oh yeah, it's pretty good at figuring out what you want.
But that can also lead to problems if you're not careful.
Definitely. So Java has these rules for how it converts types based on something called type promotion.
Hmm.
Basically, it tries to preserve as much information as possible. So it'll convert a narrower type to a wider type.
Okay, so like an int can be converted to a long without losing any data.
Exactly. And the same goes for converting any integer type to a double.
But what about going the other way? Like a double to an int?
Ah, that's where you have to be careful, because you could lose precision.
Like if you have a double with a fractional part and you convert it to an int, it just chops off the decimal.
Yep. And even converting a long to a float can cause problems because floats have limited precision.
Right. They can't represent every single long value exactly.
So you have to be aware of these potential pitfalls, especially when you're dealing with sensitive data.
And that's where explicit typecasting comes in.
Exactly. That's where you basically tell Java, hey, I know what I'm doing. Convert this type to that type, even if there might be some data loss.
And you do that by putting the target type in parentheses before the value.
Right. Like int n equals parentheses int, close parentheses, 3.75 semicolon.
So in that case, n would end up being 3.
Yep. It just truncates the decimal part.
And if you need to round instead of truncate, you can use math.round.
Yeah, which gives you a long, so you might need to cast that to an int afterwards.
And there's also a special method for converting a long to an int safely, math.toIntExact.
Ah, yes. That one's great because it throws an exception if the long value is too big to fit in an int.
So it prevents those silent overflows we talked about earlier.
Exactly. It's another example of writing code that's super robust and doesn't just fail silently.
Okay, let's move on to relational and logical operators.
The bread and butter of comparisons and conditional logic.
Yeah, the double equals, not equals, greater than, less than, all those.
And of course, the logical and or are and not.
But the interesting thing about those logical operators is the way they do short-circuiting.
Ah, yes. That's an important optimization, and it can also help you avoid errors.
So explain how that works.
Sure. So with the logical and operator, if the first operand is false, it doesn't even bother evaluating the second operand.
Because it already knows the whole expression is going to be false.
Exactly. And the same goes for the logical OR operator. If the first operand is true, it doesn't evaluate the second operand.
So how does that help you avoid errors?
Well, let's say you have an expression like n not equal to 0, a and d, some calculation that involves dividing by n.
Okay, I see where this is going.
Right. If n is 0, the first part of the expression is false, so the second part, which would cause a division by 0 error, never gets evaluated.
Oh, that's clever. It's
Right.
like a built-in safety mechanism.
Exactly. And it's something that interviewers might ask about to see if you understand those nuances.
Okay, and then there's the ternary conditional operator.
That question mark colon thing, it's like a shorthand for an if-else statement.
Yeah, it can make your code more concise but it can also be a bit harder to read if you overdo it.
True. It's best used for simple conditions where the logic is very clear.
Okay, last but not least, let's talk about bitwise operators.
The ones that work directly on the bits of integers.
Like A and D or XOR, not T, those kinds of things.
And the bit shifts, left shift and right shift.
Now, these are getting into some pretty low-level stuff. Do you actually use them much in everyday coding?
Not all the time, but they can be super useful in certain situations. Like if you're working on something performance critical, or if you need to manipulate data at the bit level for some reason.
Okay, give me an example.
Sure. Let's say you want to check if a particular bit in an integer is set. You can use the bitwise A and D operator for that.
Right. And the bit shifts are basically like multiplying or dividing by powers of 2.
Exactly. Left shift is like multiplying, right shift is like dividing. But it's important to remember that the shift amount is taken modulo 32 for ints and modulo 64 for longs.
Meaning?
It means that if you try to shift by a really large amount, it'll wrap around. Like 1 left shift 35 is the same as 1 left shift 3.
Oh, that's good to know. So it's not like you can just keep shifting forever.
Nope. And finally, we have the big guns. BigInteger and BigDecimal.
Those are for when you need to work with really big numbers, right?
Exactly, like numbers that are too big to fit in a long or a double.
So like you'd use them in cryptography or something.
Yeah, cryptography, scientific computing, any situation where you need arbitrary precision.
But there's a trade-off, right?
Yeah, they're slower than using primitive types because the calculations are more complex.
So you have to weigh the need for precision against the performance hit.
Exactly. And you can't use the normal operators with them. They're objects, so you have to use methods.
Like add, subtract, multiply, those kinds of things.
Yep. And there are some special methods for creating them too, like BigInteger.value of and BigDecimal.value of.
Okay, so we've covered a lot of ground here, from basic operators to advanced number types.
And we've really focused on the things that interviewers are going to be looking for at the senior level.
Right. It's not enough to just know the syntax. You need to understand the nuances, the potential pitfalls, and the best practices.
Exactly. You need to show that you can write code that's not just correct, but also robust, efficient, and maintainable.
So as you prepare for those interviews, really think about the things we've talked about today.
And try to come up with your own examples of how these concepts could play out in real-world scenarios.
Like, how could a seemingly simple arithmetic operation or a type conversion cause a major bug in a complex system?
Or how would you design your code to prevent those kinds of problems?
Those are the kinds of questions that will really impress an interviewer.
And show them that you're ready for the challenges of senior-level software engineering.
All right, thanks for joining us for another deep dive.
Until next time.